because before I had mentioned that I'll record these, and even though we're doing the exact same class time, I'm still going to record them because I had mentioned I would. So I want to be consistent with that. And I will load up. Let me load up the correct thing here for OS class. Actually, before I do that even, let's take a look where we're at. Do a couple housekeeping things first, and then we'll get to the lecture and talk about the lab as well. This thing does not remember my password ever inside of this program. Okay, so operating systems class. Today we're talking about threading. I have a feeling that we're a little bit behind. Really, this week we were supposed to be talking about process synchronization and semaphores, which is the content of chapter 5. So yeah, a little bit behind, but I think we can get caught up. I'll probably adjust this. We had a bit of a buffer in week 14 where we're going to be getting to cloud stuff, but that's sort of extra content anyway, so I'll probably move this stuff up, and it'll balance out the schedule. Because today I'm going back over threading due to the technical fiasco we had where my power went out, and because my power went out, the video stopped recording, and it didn't like that, so it corrupted the file. So we're going to go back over threading today. The other thing to mention is the lab. So here, if you go under week 10, you'll see lab 10. And here, what you'll want to pay attention to in the lecture is, how do you actually do this spawning of threads? We've talked a little bit about shared area of memory. We'll talk some more about that. But basically, I've got two functions, and what I'm going to want to have happen is the shared memory in this case is really just this. That's all I mean by shared memory. It's just a global that's shared between the two threads. So we will then create two threads using, that happens once in a while. I don't know why, but it loses my my web page, but oh well. All I was showing was, it's not really that important. All I was showing was the two functions in C++ that are going to be used to create two different threads, and we'll show that again in the slides. So let's go ahead and get into the slides. Oh, it's saying it can't load it. That's weird. It's the first time I've gotten that. Oh, come on. Chip 04. Okay, I might have to share my screen here then, since this isn't working very well. I'm not sure why. Hold on 1 second. Okay, I'm going to re-download it because that one didn't load for some reason, so I'm going to try that again. Okay, this time it's working. Should be loading momentarily here. just takes a second to load, but it'll come up on your screens as soon as it's done loading. I don't know why it's taking, quite exactly why it's taking so long, but what in the heck? Okay, now it's finally coming through. Oops. It is not opening the right thing. It started opening some data structures content. Not sure why. That's the problem. Okay. Okay, at least it's loading the right thing right now. It's loading the 46 different slides. We'll go through these today. So this is all of the chapter 4 content. Someone figured out how to use the drawing tools, I guess. That's awesome. Okay. Okay, here we go. So, threads. Now, threads are really just a way to run programs that are a little bit more lightweight than what you think of as a process. We'll talk about how threads relate to multi-core, as well as what various multi-threading models exist, various libraries. We do want to talk about at least p-threads, which you need. You need this guy for the lab. We will talk about some Java threading because I realize that threading, it's an important piece, it's an important topic, and unfortunately it's not quite often given in the form of CS256 or 356, so I want to be sure we cover that a little bit as well, and then talk a little bit about the high-level details of how this works and so show some examples. So as you probably realize, most modern applications are multi-threaded. The purpose of a thread is to run inside of an application, but as I said, it's a little more lightweight. You should think of process creation as a heavyweight thing, which runs a program, and thread creation as a lightweight thing. So process creation is heavyweight, thread creation is lightweight. By this, what I mean is when you spawn and create a new process, you're creating an entire structure with all the memory trappings and the heap and everything that goes into that process. Whereas a thread, which can share whatever already exists on the process. So sort of at the top level, you've got the process, then you've got the thread. So you can create threads within a process, for example. Now, in multi-threaded server architectures, this is one example of one good example of basically how threading can work. What you can do is you can have a server set up to listen for various requests from a client. So if you think about, a web service like a HTTP daemon or something like that, those are all basically requests to the HTTP server saying, oh, we want to display a page. What's going to happen is the server is going to create new threads to service each one of those requests. So for example, let me just draw this out. So request 1 comes in, server says spawn a thread to handle. But now the idea of if request 2 comes in, server doesn't use same thread, makes new thread. So we're going to have a whole bunch of threads created. We're going to have a thread, 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 all of these representing individual requests. The benefits here is that it allows for the web server that we're talking about, the hypothetical web server, to essentially be responsive, because we basically say continue your execution, continue your listening for clients, and often some separate thread handle that request. So handle the updating of that page or handle whatever it is that's being received from the service. It allows us to easily share resources, and it's a very sort of economic approach to programming, because if you think of a service, let's draw this out. We've got our service. Any given service is going to have, by definition, a bunch of things that it's serving. So this is like, for example, Ben's browser. This is Bob's browser. We want these to be responsive, and we want to share resources because the service itself, the server, knows how to dish those things out. But we want each to be assigned to a thread. So this is like going to be, for example, a thread here. Thread created, thread created, thread created. Respond to each of those. Now this gets into multi-core programming, because there's no reason that this has to only be for, say, a web service. In multi-core and multiprocessor systems, you have a bunch of cores, right? You've got core 1, core 2, core 3, whatever, and each of these can have multiple threads. Thread on core 1, 2, 3. For that matter, they have multiple processes on multiple threads, right? So very quickly, this becomes a good model to use. In multi-core programming, you can then say, well, I'm going to program this such that it can have multiple threads, which is a whole separate sort of area of concern, because once you make this decision that you can have all these threads and all these different cores, you have to then decide how are they going to share memory. So I'm actually working on something at work right now with my contract gig, where basically we are sharing memory, between multiple threads. So this is a normal thing that happens all the time. I mean, basically the idea is you've got your separate parts of the program. In this case, it's a drone application. And we're doing some virtualization with it. So we've got some sort of training simulations that interact with this this larger scale drone application, which is itself basically it's a controller for these drones. This is not showing up very well, training sim. These two things, the training simulation that we're creating, for example, teach new pilots how to how to essentially fly the drones. What happens is the drone controller has some memory for what it should be doing, but then the training sim is a separate package. So this is multi-core programming because it's a separate package. Actually, technically, it's known as VBS3, which you can look up. It's the game engine that Arma uses. So we're using a game engine. And then there's this idea of a shared memory here. So I guess my point is that, oops, this is not just an OS topic. This is a general programming topic. And you have to at least understand the high-level concept first before you get into the low-level details of, well, how do you actually go about doing this? So very important stuff. And what you have to particularly be concerned about is how do you do programming when you have this kind of a structure? How do you make sure, for example, that in our drone app we can have a bunch of threads running and they're communicating with the overall controller app? How can we make sure that they're using that same memory? And that's some of the stuff that we're going to talk about today with the technical details of it. Limit to how many threads are allowed per process, Oscar is asking. There may be some physical limit inside of the OS. I'm not aware of them. I've never run into the problem of there not being enough. I've never run into a capacity issue with that. I'd imagine there is, but it's very high. So it's not like when you think about CUDA programming, for example, and you have a bunch of CUDA cores. Well, in that type of programming, there's all these multi-cores, and they're all responsible for a bit of the graphics. And there you have very real limits, like you have 1,000 CUDA cores or something like that. But with threading, it's some high number that generally doesn't become an issue. Now, obviously, that gets into if it's actually a hardware thread. That would be so 10,000 processes. Yeah, I mean that's sort of, I mean, you're looking at some large number like that. That's gonna top out, and if you've got a server situation, that might actually be something you have to look up in the documentation for that OS and see what the limit is on it. So my answer is yes, there's going to be some limit. I don't know what that limit is. It's all going to be very OS specific, hardware specific. But it's going to be something that normally you don't have to worry about too much at the low level. But in certain domains, you will have to worry about. Like if you're doing back-end server programming in that nature, you might have to worry about it. So one of the things we got to worry about here is concurrency and parallelism. So if we're doing concurrent execution, these are all in time steps, right? So it's thread T1 runs, then T2, then T3, then T4, and then that process repeats. That's a single core system. If you allow for parallelism on multi-core, you can run thread 1 and thread 2 at the same time. This creates the issues that I was talking about, where now thread 1 and thread 2 are running at the same time. So you get into things like synchronization issues, which is what comes up in Chapter 5. And how do you make sure, for example, that if thread 1 and thread 2 are using some memory, how do you make sure that they're not stomping over each other? So that becomes a very real issue that you have to address. So in terms of processes and threads, obviously a single-threaded process, when you create one, it's just one thread. Usually there's an ability to create, in most OSs, multi-thread processes which allow you to spawn one thread, two threads. This is 3 threads, right? So each one of these threads now has its own register, its own stack, but it shares data, it shares the files, and it shares the code. So that's the interesting part of the way threading works, is that it shares that, but yet it has its own registers and own stack. Amdahl's law is This is a misplaced slide. I remember this from when we went over this yesterday, or the day before, rather. We'll get back to that. So user threads are, there's user threads and there's kernel threads. So in a user thread, these are P threads, for example. This is what you're going to be doing in the workshop, in the lab. These are just threads that programmers create. And then there's also the idea of kernel threads that are supported deep inside of the kernel. And ultimately, a P thread will create a kernel thread, but it's like a wrapper around it. As far as threading models, old school models were such as many to one. I'm not going to spend too much time on this, but basically the idea was a single kernel thread could create multiple user threads. One to one, where it was is the main approach, which is where you have a kernel thread that's spawned off. The user thread is at the top of it, so that's why I said it's like a layer, and then this goes down to the kernel thread. Solaris used many to many, which allowed you to map basically kernel threads onto any of these user threads in a many to many model. And I usually skip the 2-level model, so don't worry about this for studying. This is just for earlier versions of Solaris that used this. Kind of not a point anymore. Thread libraries are APIs that we use, so we're going to be using pthread and POSIX library for managing and creating threads in Linux. This library exists in user space, but yet it uses the kernel threads, similar in the one-to-one method I showed you. So finally now, pthreads. This is what you're going to be using in the lab. This is a POSIX standard, and these are common in a variety of Unix operating systems. Here's an example. So this code, you should be actually able to use some of this code for your lab. The idea is that we've got a void star pointer here, so this is a function pointer to a function called runner. Sum is the data shared between the threads. So this right here, it doesn't say this, but in the sense of what I'm asking for labs, this is the shared memory. Well, I guess it does say shared between the threads. So that's the shared memory. Really, it's just a global though, right? I mean, it's just int sum. It's just a global. We have a few housekeeping things here, like the thread identifier, which is the ID of the thread, and the attributes for the thread. This is showing argc, which is the number of arguments that are given to the command line when you run this program. It's just basically saying you have to run it as a.out with an integer value, and it's going to spawn that many threads. So what it does here is we call pthread init on those attributes, and we'll get back to attributes in a bit. You need to initialize this, and then you need to create it. To create it, you say pthread underscore create with TID, which is the pthread ID that I mentioned from the previous slide, with attr, which is from here that you did your init on, with a function pointer, which goes to runner. This goes down to runner. And argv1, so that's a number. That's a number that's input at the command line. I'm just going to say this from command line. Right? So from the command line, we get the argv1, sends it to runner. Now, the structure that is happening here in this program is main thread spawns end threads, child thread 1, child thread 2. That's what this program is going to do, because you'll see here there's a for loop that goes to the upper is ATOI just converts this void star into a integer. So it goes up from there on up and starts at sum equals 0. So we say I equals 1 to upper, and then sum is just printing out basically the result of how many of these you've created. Then we say pthread exit, and I'll talk about the pthread exit, but that basically rejoins the threads up. So pthread exit, actually let me talk about that now. So this for loop here goes through and sums all of these up, and then pthread exit is called, and that exits the entire thread. Then, so what we're effectively doing here is just a dummy function that's just summing things up. So it's just a dummy little runner that really is kind of pointless, but the important part is on the next thread here. So this is just a function. This could do anything you wanted. Point is to take some amount of time. We're just going to run a for loop, and it just takes some amount of time. This is the real work here inside of the this is actually inside of where the heck is it? Oh, this is inside of main. So we're back to main. Or is just this might be just a global. Nope, it's inside of main. So then we're going to go back and we're going to create our worker threads. We're going to say pthread join workers. So this is going to do all of the this is going to join up all of the threads that have been created, and it's going to join up 10 of them actually for a number of threads. Actually, wait a minute, I'm sorry, I screwed up. This example is separate. So this runner is literally just saying create a runner, sum up a bunch of stuff, come back to it. I got my two examples confused. This example here for creating 10 threads literally just creates 10 threads with null as the function that's going to be run. Because if you see the difference here, pthread create runs runner as this example. Pthread join, this is where you would put the function if you were going to run one. But instead we just put null, so it just creates our thread with nothing going on inside of it. I usually skip the Windows threading and go right on to Java. So Java threads are managed by JVM, which is kind of nice. It's a little bit simpler to use than what we're doing, which we're doing Linux stuff, and you're going to be using commands similar to this in the lab, like pthread create to create your threads. And remember, for the lab, you're essentially responsible for creating 2 threads and then having memory that communicates between the 2 of them, which is a pretty simple task. Actually, it might sound complex, but really you've got the 2 functions and you'll define each of them similar to what runner is here, like function 1, function 2. I think I already have stub functions for those in there for you. You call pthread create with function 1, function 2. Inside of function 1, function 2, it's going to manipulate that memory, and then you're done, basically. I mean, closely done at least. You have to make sure that that's reading the memory, but other than that, you're pretty much good to go. So it's not as complex as it seems, but even more simple is Java threads, because Java threads are a little bit easier to, I think, to understand, because all you really do is you basically say that it's runnable is an interface that can be extended. So you extend the thread class and then you implement runnable by creating a run. The way that works is we'd say implement runnable, right? So when we implement runnable, we create this run method. The run method, instead of the function pointer stuff that I just showed, where you were creating just these 2 functions and they just got the void stars on them, here we create a function called run. That way, when we create the thread, we give it the class summation. Summation the threading system inside of Java knows that it should be looking for a function named run inside of whatever was created for it, essentially. You can see that in the next slide here, which is the driver. So this has a main as a sum, and then a new thread which is created, which is for summation. Summation has the run, so it's going to have the run method. And since we're creating run, one thing different to Java is when you do pthread create in Linux, it automatically runs that new function of whatever you point it to, whatever void star you point to. In Java, you create the thread, then you have to run start on it, and that starts the running. Now, you don't get results back from that until you call join, because basically the way this is working, and I'll get into this in a couple slides here, is basically you've got the start, and then you've got join at the end of it. Oops. I don't know why that's okay. Start, and then join. So when it's done, we want it to join back up with the other threads. So it's going to join, and join is basically saying when we're done with that function, that run function, we come back to the parent, report our result. So it's like you're basically saying that's the exit function. One thing growing in popularity, this is sort of getting back to some of the theory, is implicit threading. Your compilers will implicitly thread your code that is not dependent upon each other in some cases. It's smart enough to do that to optimize and make your programs faster to run. In many cases, that's done implicit and hidden from the programmer, so they don't even have to worry about it. Another thing that's a popular trend in threading technology is thread pools. This is kind of related to actually, for those of you in data structures, or not data structures, software engineering this semester, we were talking about object pools today. This is similar. This is basically the exact same idea. The idea is you create these threads in a pool and they just wait for work. So they're created at the start time. That way, and it's really nice because that way you don't have the baggage of the creation of that thread, which could take a while. I mean, by a while, I mean, 100 milliseconds or something. I mean, it's not a huge amount of time, but, it could be a couple ticks if it's a very lengthy process creation. That would be extremely rare for it to take even that long, but still, it could. So you create a thread pool, you create all those threads at the beginning, and then whoever requests them can get them. So I usually, let's see, OpenMP. OpenMP is for parallelization. These are compiler directives that allow you to create threads in parallel. So if you're using OpenMP, you're basically realizing that, okay, this region, for example, can be run in parallel. Now, once that's done, we're going to go back to sequential code. So this entire region can be run parallel to each other, which is what OpenMP allows you to do. We're not going to really do anything with OpenMP, but I just wanted you to be aware of it, that it exists as a way of allowing you to optimize your threading. So certain threading issues exist. Fork and exec basically are two ways of doing things. Remember, this is from several weeks ago. We talked about fork and exec. So the question is, does fork duplicate only the calling thread or all threads? Most versions of Linux these days have two versions of that that vfork, for example, and fork, which you can have some that duplicate the calling threads or don't, for example. So usually if you need to work on that, that would be a situation where you want them to duplicate the calling threads, then you would have to look into something like vfork. Exec works by basically replacing the running threads, including threads. So this exec actually works to replace all the threads that exist in that process, as you would expect from exec, because exec essentially takes over that entire process, and the process includes the threads beneath it. So it just replaces that. Now, we talked a little bit about signal handling a few times ago. Signal handling is used to notify processes that events have happened. You usually do this with a signal handler that's designated as a function that exists, and when that signal is received, the function is fired. Kind of an event-based approach. So the question becomes, when we're dealing with signal handling, where does that exist inside of a multi-thread program? We can either deliver the signal to the thread by which it applies or to the process. Those are all operating system level decisions. Now with Linux, it's going to deliver it to the thread that spawned the intended, it's going to do option A here, deliver the signal to the thread which with it applies. So a couple general approaches to thread cancellation. When you do a pthread create, as I said here, this is something you're going to be using in lab. You do your pthread create. You can cancel it at any time. There's two methods to do that. Either you asynchronously do it, which means you cancel it right away, or you wait at a certain time, as which then you can cancel it. On Linux, thread cancellation is actually handled through signals. So it's more of a deferred cancellation situation in Linux. There is also something called thread local storage, which allows you to, instead of having, remember we had that picture where we've got the threads with their registers. This is our data, right? And this is our T1, and this is our T2. And each one of these individually is a register R, for example. I don't know why the heck that isn't working. I'm trying to draw R in there here. I'll just do it this way. That's our R value in each of these. So the registers are here, but the data is shared. Now, if you don't want to do that, you basically forget that and you use TLS. This allows you to have different local variables, and it binds that data essentially to that thread. And if you want to use that, we're not going to do any of that in class, actually, in lab. It's just too much to do, too little time. But Linux does support TLS. You can look it up in the man pages. So here's some scheduler information. We're going to get back to the scheduler soon. It's not really the topic of this week, but we do require that there's some scheduling that has to happen once this process and thread are created. We then have to say, how does the scheduler activate those calls? And so that's the subject matter of like chapter 6 and 7, for example. And so I'm going to skip the Windows stuff as I usually do and go to Linux. Linux refers to most of these things as tasks. And you can actually clone. So when you do your pthread create, if you want to create instead a kernel level thread, you would use clone. and it uses the task struct to actually create that kernel level. So everything we've talked about up to this point has been user level threads, which is where we're going to play in. But if you want to use kernel level threads, you could reference this, but that's not what I have you doing. Let's talk about what I do have you doing. And then we can start wrapping up. Yeah, this program is not perfect. I don't know why it decided to kick me out of the browser before. But anyway, what I was trying to show you early on here was the lab assignment. So we're through the slides now, and basically the pthread create calls that you saw in the slides, it's my intent that you would create 2 of those here with those functions. We're not going to do mutex locks. So that means that you would do your joins right after your creates inside of main. Therefore, this is a dirt easy lab. All you really have to do is you do your creates, you do your joins. You have these 2 functions that modify the global. And if you want to go really crazy, you can put some prints in here to see what the values are. In fact, that's what I would encourage you to do. I don't have that as a requirement for the lab, but just for your own sanity, you might want to throw some printfs in here to see what the values are coming out of that shared memory. And that's about it. So the core content you'll want here is in the pthread example. So I've got that online now in the PowerPoint, and then you've seen it in the video and in our interactive session here. So yeah, good question, Oscar. About the max threads, there is one. You'll have to dig the research and see what it is per operating system. Are there any other questions we have today? The lab is due Friday, I think I put on there. It's pretty. Yeah, I put the 7th. Someone's already turned it in, so it's pretty. As I said, it's pretty basic. Just reading through the chat. Returning values to the screen with multi-thread has always been a headache. I'm not sure, Mark, if you're referring to like the timing of it, perhaps. Because I suppose that, yeah, that can be tricky because you don't know what to display to the screen until the thread is done computing the value. So that can be tricky. And in the meantime, you can, for example, a lot of times what people will do in the application that I've been working on a lot these days, since we don't know what the value is yet before that thread comes back to it, we just gray it out, or something, some way to tell that value hasn't been input yet. So that's actually a really good point. Something we usually don't talk about in academics, but yeah, I think that if you're in that situation, you got to figure out something to do with the UI until the value is returned from the thread. Oscar, so pthread, the pthread create that you're going to use right here, that is given. This is starting to look messy here. Anyway, it's pthread underscore create TID. The TID is back here. That's a pthread identifier, which is basically just an enum value. And then attr is your attributes. Runner is the name of your function that you use. That's a void star function. You can put that function anywhere you want, basically, in that file, because the way C++ and C works is when you say runner, it's going to assume that that's just some reference, and at runtime, it's going to find it, and it's going to find void star runner down here. You do have to pre-declare it up here, so make sure you do that. If you want, they put it below main. If you put above main, then you don't have to pre-declare like they do. This here is a pre-declared runner function right there. So hopefully that helps give some clues there. I have had some thread creation examples I've given before that should be in D2L as well, earlier on, like several weeks ago. So if you want to take a look at some of those, I think it's in the I guess I can't remember if it was week 3 or week 4 week 5 examples, I think has some. So Oscar is saying, I guess what I'm asking is, we're not restricted to just that one function, right? The function call can call their classes and functions. Yes, certainly. The function you call, that's like your main, essentially, for that thread. It just runs that off as if it was main, essentially, and that's the starting point. So it's fully anticipated that from there you would call other classes, functions, instances, whatever else you're going to do. Good question. So yeah, when you're doing your threading homeworks, or your homework, your lab, I'm sorry, not your homework, your lab, there is something to keep in mind. I'll dig it up and I'll put it on. So I can't recall offhand. It's so when you do your GCC command, I want to give you this little tip. There's a certain command you gotta do. Let me look it up quick. Here's a good example. I'm going to post this in the this should be it. Post this in the chat. Let's say you have a program called myprogram.c. Wow. Thanks for the info, Mark. No, I don't know what's going on. Yeah, no idea. Maybe it's my slight cold I still have from drywalling. Got a bunch of, I drywalled without a mask, so I've got all these sinus issues. It could be that. Last time I ever do drywall without a mask, I'll tell you. Anyway, all right. Cool. So on that note, I guess we're good to go. I'll post this online for those of us that couldn't make it. Yeah, so I sent a note out. Again, we don't have class Monday due to my son's surgery, which is Monday. We will have class Wednesday. And I'll keep you posted. I'm feeling like I'm going to want to record some kind of a video or something to get us caught up. Unfortunately, it can't really be a required attendance thing like this is, because I don't want to put any stress on people's schedules where they think that they can't make it because they don't have a time scheduled, etc. But what I can do is maybe try to get us caught up via videos and things like that. So I'll be working on that in the next couple weeks, and we'll get caught up. So as always, let me know if you got questions on email or whatnot, And we will see you in software engineering class on Friday if I've got you. Otherwise, we'll see you later. Oh, and thanks for the positive thoughts, Dan. I appreciate it. We will talk to you guys later.